Hi, this is Jordan Stevens and Danica Dvorak. Sadly, we couldn't do our presentation together this week because of spring break, but we're going to be going into it. What we're going to be talking about is Chapter 3 of the book. The first section is 3.1, Inversion of the CDF. This is for a continuous example. They gave a continuous and discrete examples. Let's say that we have a x that is continuous random variable that is generated from continuous random CDF with the function f, and that we have a random number between 0 and 1 that's uniform. Then the inverse of the f function, whenever you plug in a uniform random variable, will generate the CDF of f. This allows for the generation of invertible CDFs, and since the range of the CDF can map to the random variable, then this is plausible. So basically what we're saying is that the y's plot all of the x's, and that the x's are plotted from the y, and they encapsulate it. Some things to note in this section is that it has to be invertible. Only a certain few CDFs that are continuous are invertible. They give a few examples in the book. The main one probably is the exponential distribution. That's the example they gave. So going into that, here's the example. Let's say we have a continuous example for the exponential, and we have this function, lambda e to the negative lambda x, and it is on support from 0 to infinity. So let's say the solution to this would be if you were to have the f of x function, and since it's going from 0 to infinity, we need to take the integral, so this would be the complete area of the function, and it gives this formula right here, 1 minus e to the negative lambda x. Now from this, we're going to do our typical inversion step, which is where we equal it to a variable, and we solve for the x variable right here, the random variate. So whenever we solve for the random variate, it's going to equal the inverse as when it relates to r, and r is a uniform variable. So we get negative 1 over lambda ln of 1 minus r. Now if we were to run this and run random uniform variables and as the r here, then we would generate the CDF of this function right here. This is very powerful because it is often kind of hard to generate a CDF of a function just from scratch, but this is the way to do it. Moving on, we're going to go to our discrete example. If x is a discrete random variable and support 0 until the ending of it, suppose there's a CDF function f for x with a random number r is uniform between 0 and 1. Same as the last time, except there's going to be a different function that we need to generate. So the function w is the min of x, where or r is less than the function of x, where x goes from 0 to infinity. This little x is just the variable we put in place that is the y variable in relation to the x to random variable. This will generate the CDF for f. Same thing is that we need to make sure that it's invertible, and last, we also know that the range will map to the x, and it is plausible. So we'll have another example here. This is a discrete formula where it is theta to the x minus 1 and 1 minus theta times 1 minus theta, where x is 1, 2 counting numbers, and theta is between 0 and 1. Now if we take the formula here, instead of using the integral, we're going to be using the sum function. Since it is not continuous, we don't use the integral, and since it is discrete, we're going to be using the sum function. We get this right here, this formula right here, and from this, we need to plug that formula into the w function, where w is the x random variate, and it is the min of x, and r less than 1 minus theta to the x, where x is generated here. Right? So from this, we do need to invert this function right here to solve for x, and once we do that, we get this function right here. So it does still need that inverting step. It just needs to be encapsulated in this W function. Now, if we were to generate this, then we would get this function right here, which is a floor function of the ln of r of the ln of theta plus 1. Moving on to 3.2, second section. Let's say that we have a function that is not invertible, unlike the ones previously shown. It can't be solved analytically, it can't be solved mathematically. Then to actually solve that and actually figure out how to generate the random variate, we need to find another invertible probability function and use it to map out the function that's not invertible. So we have an algorithm. Let's say we sample independent variates y from g of y. G of y in this function is the invertible function, and h of y is not the invertible function. So we know that g of y can be inverted, so we invert it. We take the steps to invert it. And we have the random number that's uniform between 0 and 1. And then we do this little function right here, which is the real crux of the envelope projection. If the random generated number is less than the y value, or the output of h of y and g of y at r, then we accept it. But if else, we reject it and just keep going. So this allows for a rejection. So it allows for acceptance and rejection. The accepted values will generate the CDF of the function. So let's go and do a example. Let's say we want to do the standard normal distribution. It is not invertible analytically. So we're going to take the exponential, which we have shown previously in the section 3.1, that we can invert it. So we're going to take this function as the h of x, and we're going to take the g of x as the invertible function, the exponential distribution. Now, we need for the g of x to be as close to h of x as possible. And we also need the g of x function to be larger than the h of x function at all x's. So it needs to majorize the h function. So let's say we have the lambda value or the k value. We need to multiply the exponential distribution to show that it is as close as it possibly can to get to at h while also being bigger than it. For this, we need to solve for a k variable right here. And this just shows how we solve for the k variable here. It's kind of just a few steps, easy steps. Once we go to this, then we're going to take it to the actual formula to be used. So now that we have the new lambda function right here, the exponential function, and we have the h of x, we form a ratio by doing the integrals of both of them. And by doing the integral, we get this ratio right here. Once we have this ratio over here, we know that for e of x to majorize this while also being as close to this, we need a lambda of 1. It makes the most sense. So plugging in lambda 1, we get the g of y getting this, which is the bottom half of the section. Generating from that, we generate our formula, which is this one right here, e to the negative y minus 1 squared divided by 2. And we need to check if the random variate is less than it. So generating from this and going down to the section below, taking the ln of both sides, the log of both sides, so that we can get that e variable out of it. We have the negative ln of the random variate is greater than 1/2 y minus 1 squared. Doing this, we'll generate this graph right here. And basically what we're doing is we're taking random variates and we're plugging it into this function on the top. And if the function passes, then it will kind of move into that bottom function. So we're using the top function to sort of emulate the bottom function right here. And moving into our last section that we have for this is 3.3, ratio of uniform methods. Let's say that we have two uniformly distributed random values. So we have a u that is uniformly distributed between 0 and 1, and we have a v that is uniformly distributed between negative a and a, where a is a positive integer. We can create a new random variate x equals v divided by u from these two. This is a jointed probability. So we have the theorem here, let h be any non-negative function with h of x dx is the first one, so the uniform. And let C, which is our random variate, x, be of the UV joint probability or the 0 less than u. Oh, sorry, my fault. It is the joint probability where u is between 0 and the square root of h of v divided by u. And where v divided by u is on support of h. So this basically means vu is inside of the h function we have, and let the point uv be uniformly distributed over C. So this is kind of using the two formulas that we had previously. We're using envelope projection, and we're basically, instead of plugging the x variable in, we're plugging in the jointed probability of v divided by u. And we can generate a new probability density function from the ratio of h of x divided by the integral of h of x. So with that, it concludes these three sections for chapter 3.